Works on my machine is a phrase that every one of you will say at some point. It's worth examining because there is no single cause behind it. The problem could be a different operating system or library version, an environment variable set only on your machine, a system package that happens to be installed, or an old configuration file you forgot existed. Any one of these differences is enough to make identical code behave differently on two machines. Virtual machines and containers both help package an environment with your code, but they solve the problem at very different levels. A virtual machine simulates an entire computer, including virtual hardware, and runs its own independent kernel. This provides strong isolation, but it comes at a cost. A VM takes time to boot because it must start a complete operating system, and its disk image is often several gigabytes. A container provides a different kind of isolation. It creates an isolated environment while sharing the host machine's kernel instead of running its own. It's also important to distinguish Docker from containers as a general concept. Docker is one tool in the container ecosystem, not the entire ecosystem. Podman, for example, can run the same container images without requiring a background daemon or root privileges by default. The concepts you're about to learn are container concepts rather than Docker-lowercase specific ones, so they'll transfer to whichever tool your lab or future workplace uses. The difference is most obvious during startup. Recall the boot sequence from week 0, firmware, then a bootloader, the kernel, and finally an init system bringing up services. A VM must go through essentially that entire sequence for its own operating system before the applications inside it can start. A container skips almost all of it by sharing a host's already running kernel. That's why a container can start in a fraction of a second, while a VM may take tens of seconds. If your computer doesn't run Linux natively, as is true for most Mac and Windows laptops in this room, you can still run Linux containers through an additional layer. On macOS, Docker Desktop and alternatives such as Colima or Lima manage a lightweight Linux virtual machine behind the scenes. Linux containers need a Linux kernel to share, and macOS doesn't provide one. On Windows, Docker Desktop commonly uses the WSL2 backend and its Linux kernel. The implementation details continue to evolve, but the underlying concepts remain the focus of this section regardless of platform, images, registries, namespaces, groups, mounts, networks, and permissions. Learn those concepts, and you can look up the platform-lowercase specific details when you need them. So what does a container actually isolate? Two separate mechanisms are involved, and they answer different questions. A namespace controls what a process can see. In a PID namespace, the first process inside a container sees itself as PID1, even though the host may identify that same process as PID 882013. It's the same process with different identifiers in different namespaces. A mount namespace gives the container an independent file system view. A network namespace provides its own network interfaces, IP addresses, routing table, and port space. That's why two containers can both listen on port 8080 without a conflict. They don't share the same port space. A UTS namespace gives the container its own host name. A user namespace can map the container's root user to an unprivileged user on the host. The process has root privileges within its isolated environment without necessarily having root privileges on the host. That final point deserves careful attention because user namespaces are useful but easy to overestimate. Inside the container, the process is root. On the host, that same process may correspond to an account with no special privileges. If the process somehow escapes the container, it doesn't automatically gain root access to the host. However, this is a mitigation rather than an absolute guarantee. Namespace isolation and kernel security are not the same boundary. That brings us to the other mechanism. A C group controls how many resources a process can use, including CPU time, memory, and disk I/O. Together, namespaces and groups provide a clearer picture of a container. Namespaces restrict what a process can see, whilst groups limit what it can consume. Both mechanisms are applied to an ordinary process running on the host. That phrase, an ordinary host process, points to an important limitation. Every container on a machine shares the same host kernel. A kernel vulnerability can potentially cross the container's isolation boundary in a way that a VM's separate guest kernel is designed to prevent. This isn't a reason to avoid containers. It's a reason to understand that containers and VMs provide different levels and kinds of isolation, and to choose appropriately for the risks involved. How is an image built layer by layer? If Git's object model is still fresh in your mind, this may feel familiar. An image might begin with a base layer containing the operating system environment and runtime, followed by a dependency layer for packages and third-party libraries, and then an application layer containing the code you change regularly. Image layers are content addressed, much like Git objects. If the inputs to a build step haven't changed since the previous build, Docker can reuse the cached result instead of rebuilding it from scratch. To benefit from the cache, order your Docker file carefully. Put steps that change rarely near the beginning, such as installing system packages, build tools, and third-party dependencies. Put frequently changing content near the end, such as your source directory, include directory, and test files. Reversing that order has a concrete cost. Suppose your Docker file runs copy.before installing packages with apt. Changing a single line of application code invalidates the copy step and every dependent step after it, including package installation. Every build may then reinstall all the system packages even though the package list hasn't changed. It's also useful to distinguish two caching mechanisms. Layer caching preserves the file system result of a completed build step. A cache mount preserves a tool's working data across builds, such as the package cache used by apt, the object cache used by ccache, or the download cache used by pip. This allows finer-grained reuse than caching an entire layer. Multi-lowercase stage builds solve a related but different problem, separating what you need to build the code from what you need to run it. A builder stage beginning with from build image AS builder can contain the complete compiler toolchain and build dependencies, followed by a step such as run make release. A separate runtime stage can then use copy -- from equals builder to copy only the finished binary before setting user app and cmd. Without this separation, a common beginner mistake is to include the compiler, full source tree, and test framework in the deployed image. That makes the image larger, slower to download, and more vulnerable than necessary because every additional tool may introduce another security risk. The starting Docker file in your Visual Relay lab is deliberately designed with these problems. It builds successfully, and it's a well-lowercase designed image are not equivalent claims. Your job is to close the gap between them. Runtime identity is another important part of hardening a container. By default, a container process often runs as root. A better practice is to create a dedicated non-root account that has no login shell, password, or administrative capabilities because it exists only to run one application. Combine that account with a read-only file system and narrow, explicit exceptions for paths that genuinely need to be writable. Add no new privileges to prevent the process from gaining additional privileges at runtime, along with firm limits on CPU, memory, and process count. These settings aren't there merely to make your composed file look complete. They apply the principle of least privilege, deny access by default, and allow only what the process actually needs. The benefit becomes clear when something goes wrong. If the application is compromised, the attacker gains control of an unprivileged account on a mostly read-only file system and cannot easily escalate permissions. These controls can turn a serious breach into a smaller, more contained incident. Running a graphical application inside a container requires a carefully controlled connection to the host's desktop session. That session uses a display server, sockets, environment variables, and permissions associated with display or Wayland display. A container doesn't receive access to any of them by default because they don't automatically cross the isolation boundary. As a result, an application in a container may be unable to see the host's display socket or may lack permission to connect to it. Either situation can produce a blunt cannot open display error. The debugging steps depend on your display system. With X11, check display, X authority, whether the correct socket is mounted into the container, and the socket permissions. With Wayland, check the runtime socket, XDG runtime directory, any desktop portal involved, and whether the application has reliable Wayland support. When you have multiple containers, they need a way to find one another. In a composed network, a service can normally be reached by its service name through DNS. This allows one container to contact another without relying on an IP address that may change after a restart. However, don't place every container on one flat network simply because it's easier to configure. You might define 3 separate networks named CameraNet, HandoffNet, and ControlNet, with each container joining only the networks it needs. This follows the same design principle as ProxyJump in the SSH section. A container's network access should match its actual responsibilities, instead of extending beyond them for convenience. A process being alive and a service being healthy are two different things, and confusing them can cause real outages. Docker PS can show a container as running even when its process is stuck in an infinite loop and doing nothing useful. The process hasn't crashed, so the container still appears to be running. A health check is different. It periodically runs a command that tests the service, and the command's exit status determines whether Docker marks the container as healthy or unhealthy. The settings interval, timeout, retries, and start period control how often the check runs, how long it may take, how many failures are tolerated, and how much startup time the service receives before failures begin to count. All of these elements come together in a compose file, which describes an entire system in one document instead of relying on a sequence of manual commands. It defines which services to run, which network should connect them, and which volume should preserve data when containers are recreated. Omitting a single parameter can create a subtle problem. The system may still appear to be running, but its behavior may have quietly drifted from the intended design. This is the central shift that Compose represents. Deployment changes from a manual sequence that someone must remember and perform correctly into a reproducible description that anyone can use to recreate the system. This should sound familiar. It's the same principle behind the systemd unit files from week 0, a declarative plain text configuration that describes a running state. One more distinction is important. Depends on control startup order, not readiness. A process may have started even though its database schema is still initializing, its server isn't responding correctly, or it hasn't acquired the display connection it needs. A health check provides a much better indication that a service is actually usable. Compose also has a defined scope. It's designed primarily for running multiple services on a single machine, such as during local development, a class assignment, a demo, or a CI job. Scheduling and rolling out services across multiple machines requires a different kind of tool, such as Kubernetes. Knowing the limits of Compose is as useful as knowing how to use it. In this lab exercise, you'll rebuild the deliberately oversized root-running visual relay image using a multi-lowercase stage build, a non-root user, and a working health check. You'll then connect the entire system with a Compose file. That's the fourth answer. Let's bring all four back together. Let's return to the question we started with. When software development expands beyond one person on one machine, what keeps the work trustworthy, consistent, and reproducible? You now have four concrete answers spanning 5 tools, not merely a collection of commands. SSH's answer is that trust must be verified rather than assumed. That's why an SSH connection checks identity in both directions. A host key helps you verify the machine, and an identity key helps the machine verify you. It's also why trust on first use makes you responsible for that initial verification instead of silently trusting whichever key appears. Git and GitHub answer that consistency comes from a transparent, reviewable history. Git identifies objects by hashes of their content and represents history as a directed graph rather than a simple sequence. When Git can't reconcile two changes, it shows you the conflict instead of guessing. GitHub adds a shared review and coordination process around that history. Together, they let a team trust how changes were made instead of merely hoping that everyone's copy matches. Curl's answer is to locate a failure one layer at a time: DNS, TCP, TLS, the HTTP status, and finally the response body. This is much more effective than treating "it's broken" as one vague problem and trying random fixes. Docker's answer is that an environment must be described and reconstructed rather than remembered. Namespaces and groups make isolation and resource limits explicit, while a Compose file lets someone else recreate an entire multi-lowercase service system from the same description. 5 tools, 4 core answers, and 1 underlying discipline. It's the same discipline your labs will require. A lab that merely runs isn't necessarily complete. Ask these questions every time. What does this system trust, and did I verify that trust or merely assume it? What is the actual boundary of what it can reach or affect? How would I detect a failure instead of letting it remain hidden for days? And if I handed this exact setup to someone else, could they reproduce it on their machine? This checklist matters more now than it did a few years ago because much of what you receive in the lab, including an SSH configuration, a Docker file, or a Compose file, may have been generated by an AI assistant. Generated configuration can be completely correct, but it can also be confidently and fluently wrong while appearing correct at first glance. Use the questions from this video to tell the difference. Is the result safe? Is it reproducible? Is it something you would actually trust? Answering those questions is your responsibility, not something you can outsource to the tool that produced the file. In this week's labs, type every command yourself on your own machine instead of simply reading past it. That's how these 5 tools will change from something you watched in a video into something you can use with confidence. That's it for this video. I'm Claude. Next time, we'll work through the next handout.